Alright, welcome to section 2.2, the derivative function. First, we're going to recall our definition of the derivative. So, the derivative of f at a point A is the instantaneous rate of change of the function f at the point A. Alright, this section is going to explain to us how the derivative is itself a function. Alright, so first we're going to do a little warm-up. So we're going to estimate the derivative of the function graphed in this figure below at all of these different points. And we're going to use our estimates to complete this table. Alright, so let's remember that the derivative is the slope of the tangent line. A tangent line is just the line that touches the graph at that point. Alright, so I'm going to use my fancy ruler tool here, and we're going to estimate the slope of these lines. So the first one is x is equal to -2. So -2 is, I'm going to use a bigger pen here, let's do blue. A little bit bigger. Alright, so this is x is equal to -2. So we're going to bring my ruler over, get it to line up-ish, alright, and draw a nice straight line. Back it up away, and we want to see, well, what is the slope of this blue line? Well, the slope is the rise over the run, right? So we can do a rough estimate of the slope by seeing how many units we go up to how many units we go over. So let's see, here's 1, 2, 3, 4, 5. I'm going to pretend this keeps going up here. 6 units up and 1 unit over. So 6 over 1, that gives us a slope of +6. Alright, let's look at x is equal to -1. That's -1 is here. So on our graph, that is this point. Again, I'm going to bring my ruler over. And again, this is just an estimation. Line it up with our graph. And let's go ahead and draw our line. And we want to calculate this slope. Alright, well, in this case we're starting off in the middle of a point here, of a square here. So we can go up 1 to the middle, up 2 to the next middle, and it looks like it crosses our next vertical line over here. So it looks like up 2 over 1 gives us a slope of +2. Alright, go ahead and see if you can complete this table. I'm going to go ahead and fill in the rest of them. So at 0 we have a slope. Well, let's go ahead and do one more so we can see this next one here. At 0, this slope here. Let's see, what's different about this slope compared to the last two that we just found? This one is negative, right? And we're going to say this looks like you go over 1 and down 1, and so therefore we have -1 as our slope. And now I'm just going to go ahead and fill in the rest. So we'll have -2, -1, 1 is -2, 2 is also -2, 3 is -1, 4 is 1, and 5 is +4. Alright, so see if you can see where I got the rest of those estimates from. So, our first question, does the derivative of f appear to be a function of x based on the table from the warm-up? why or why not? So if we remember back to one of the first sections of chapter 1, where we looked at tables of data to determine if it seemed to be a function or not. And remember, one of the important things was that a function is 1, 2, 1. Meaning we couldn't have two different numbers, or the same number give us two different numbers, right? We couldn't have one input give us two different outputs. That doesn't make any sense. We can only have one input to every one output. All right? So if we go ahead and look up at our table here, we can see that we don't have any of the same inputs giving us different outputs. So, yes, the derivative of f, or f prime of x, seems to be a function, specifically of x. All right. So problem 2 asks us to plot the values of the derivative that we just found from our warm-up to create a graph of the derivative. If derivative itself is a function, we can graph it, right? So let's go ahead and plot all of these points. So our first one is -2 and 6. All right? So -2 and +6. 1, 2, 3, 4, 5, 6. All right. Our next set of points is -1 and +2. Then we have 0 and -1, +1 and -2, +2 and -2, +3 and -1, +4 and +1, and +5 and +4. Okay? And again, these are all just from this table up here. Okay? So if we go ahead and connect these, it might look something like this. All right, and this is the graph of the derivative of the function shown here in red. All right, so based on this information, we can fill in the following table. So when f is increasing on an interval, all right, so let's go back up to our function and see where f is increasing. So f is increasing here and here, right? So it looks like f is increasing from -2, almost up to 0, right? And then from almost 4 up to infinity. All right, so we can look at our f of x values and our derivative values, okay, on those same intervals. And we can see that where f is increasing, the slope, the slope of f is positive. All right. And the derivative is also going to be positive on that interval. So again, we could come up here to take a look. All of these slopes, this is a positive slope, this is a positive slope, this is a positive slope. Okay. And all of our derivative values are positive there. 6 and +2. All right. And then same thing again for 4 and 5. We have positive derivative values. All right. So then our next line, we have f is decreasing on an interval. So whenever the function is decreasing, we will have negative slopes, and our derivative is also going to be negative on that interval. All right, how about this last line? The slope of f is 0. Well, we know that the derivative of a function is the slope at that point, right? So we could go ahead and fill out over here. If the slope is 0, then the derivative must also be 0. And okay, so the slope was positive if f was increasing. The slope was negative if f was decreasing. If the slope is 0, the function is doing neither, right? So the function is neither increasing nor decreasing. So f is constant on an interval. All right, so this table is going to be very important later. So example 3, again, we're given the graph, this time of a function g, and we're asked for which values of x is the derivative at x equal to 0. So is g prime of x equal to 0 where? So again, g prime of x is the slope at x. And if the slope is 0, so a 0 slope gives us what kind of line? A horizontal line. So we are looking for any horizontal lines that we could find on our graph. So let's go ahead and break out my ruler again. And we're just going to kind of follow the function and see what happens. All right, so we're going up. Over here, no horizontal line yet. And it looks like at our very top point here, if I could get my ruler to be super straight, it's going to fight with me between 0 and 1%. Pretend it says 0%. Okay, that gives us our nice horizontal line. All right, I'll use red here instead of the blue. So we have a nice horizontal line at x is equal to 0, right? X is equal to 0 down here. So the derivative g prime of x equals 0 at x is equal to 0. All right, is that the only place on this graph that the derivative is equal to 0? The answer is no. Down here. Oh, there we go. I got 0. There we go. Our slope is 0 at the very bottom of our graph here as well. And that happens at x is equal to 4. So at x is equal to 0 and x is equal to 4, g prime is equal to 0. All right, I'll get rid of my ruler for a moment. Part B asks us for which values of x is g increasing. All right, then there's a few other parts, but let's focus on increasing. So we already know that when we're increasing, our slopes are positive, right? We learned this in the first chapter. So on this section we are increasing, and on this section we are increasing. Okay? So g of x is increasing on negative infinity up to 0, and also 4 to positive infinity. All right, if we write this in set notation. And I'll write increasing. I'll say g is increasing. All right, so where is g decreasing? Well, g is decreasing. Make this bigger. There we go. G is decreasing on this section. All right, so G is decreasing from 0 to 4. In the last part of this question, what can you say about the derivative on these intervals? So based on our table, if our function is increasing, our derivative is positive. So we can say g prime of x is positive on those intervals. And here we can say g prime of x is negative. Again, based on the table we just filled out. All right, so based on all of these observations, which of the following graphs is the graph of the derivative g prime? All right, so when a function is positive, don't think about it being the derivative anymore, just think about it being its own function. When a function is positive, what does that mean about its location on the graph? Now remember, positive and increasing don't necessarily mean the same thing. We discussed this when we were talking about graphs towards the beginning of chapter 1. If a function is positive, it lies above the x-axis. Do we remember this? And then likewise, if a function is negative, it should lie below the x-axis. So our function, the derivative, so g prime of x, that's the function we're looking at, needs to be above the x-axis. To 4. So our middle graph here, we have this from 0 to 4, and it's above the x-axis from negative infinity to 0 and from 4 to positive infinity. One more thing I'll mention is that when the function changes from increasing to decreasing, all right, so when the function, I'll say a function, changes or the other way around. All right, so from decreasing to increasing. So let's double check that. Part A, we found that our derivative was equal to 0 at 0 and 4. All right, and here we have 0 is where our derivative is equal to 0. So that's where we cross the x-axis. And we see in our original function that at to increase, right? From decreasing. And at x is equal to 0 and x is equal to 4. And this is the best graph for the derivative in our case. All right, let's go to example 4. So below. Again, we're asked for which value of x. We're looking for those points horizontal tangent line. Alright, so we're going to have a horizontal tangent line at all of the peaks and valleys. So there, and there. We have 3 places with a horizontal tangent line. So when x is equal to 0.5, when x is equal to 2, and when x is equal to 3. Our derivative is 0. All right. Then, for which values of x is f increasing? Well, f is increasing from negative infinity up to our first 0 derivative, so up to 0.5. It's also increasing again from 2 to 3. And if f is increasing, we know that the derivative must be positive. Okay? So then f is decreasing on the intervals 0.5, 0.5 to 2, and again from 3 to positive infinity. And we know when f is decreasing, the derivative is negative, so less than 0. And again, we're asked to sketch the graph of the derivative based on these functions, or based on these observations. All right, so let's go ahead and draw some axes here. So first thing is we want to label everywhere that our derivative is going to cross the x-axis. All right, so that would be wherever it's equal to 0. It's going to touch the x-axis. All right, so at 1/2, at 2, and at 3. So we're going to label this 0.5. We'll label this 2 and 3. And so we'll say our derivative must touch the x-axis at these 2 points. I started saying touch instead of goes through because sometimes we'll just bounce back immediately, but it's still going to touch the x-axis, okay? F prime of x now. So we need to see where is it positive and where is it negative. And I'm going to create little dotted lines to help us think about this here. All right? So our derivative is positive, which means above the x-axis from negative infinity up to 0.5. So this is positive in this little section. All right? It's also positive between 2 and 3. So in this little section. From 0.5 to 2, it's less than 0, so it is negative, which means it's going to be below the x-axis. And from 3 to positive infinity, it's also negative and below the x-axis. So if we want to connect these 3 points and stay positive, negative, it will look something like this. So positive means above the x-axis, negative means below the x-axis, then we have to be positive again, and negative again. All right, so this could be a graph of what our derivative looks like for this function. All right, example 5, and this is our last example for today. The following table gives the values of C of t, which is the concentration in milligrams per cc of a drug in the bloodstream at time time t in minutes. All right, so we have this little table here. Part A asks us to estimate the value of c prime of 0.1 and to give units and interpret your answer. All right, so far the best way that we have learned to approximate or estimate the derivative is just to look at the average rate of change, right? So c prime of 0.1 is approximately, that was an interesting squiggle, approximately the function c of 0.2 minus c of 0.1 over 0.2 minus 0.1. So we're looking 0.1 to 0.2 on this interval. All right. Again, this is not going to be the actual instantaneous rate of change. This is just an estimate, okay? So based on this table, c of 0.2 is 0.94, and c of 0.1 is 0.89 over 0.2 minus 0.1, and we get the answer is 0.5. Units would be our milligrams per cc per minute. All right, and because it's positive, the concentration is increasing since the rate of change is positive. Okay, so that's our answer for part A. Part B asks us to estimate the rest of the values, so we can just fill in this table. Okay, so I'm going to do one more calculation and then I'll let you fill in the rest while I just fill in the blanks in the table. Alright, so I'll do the estimate the derivative of 0.2. Alright, so that's c of 0.3 minus c of 0.2 over 0.3 minus 0.2, and that's going to give us 0.98 minus 0.94 over 0.1, and we'll get 0.4 milligrams per cc per minute. All right. So we can now fill out two of the open spaces in our table. All right, so we estimated the derivative at 0.1 to be 0.5, and now we estimated the derivative at 0.2 to be 0.4. Alright, so I'm going to go ahead and fill in the rest of these values and leave you to do the math behind it. Alright, so we have 0.5, 0.2, 0, negative 0.3, and negative 0.7. And we're just going to make a few final observations about this table. Alright, so I'm going to move this work down, just get it out of the way. So we're just going to make a few observations like I said. From time t is equal to 0 right up until t is equal to 4, our derivative is positive. Okay, and we notice that it starts out large and it starts decreasing towards 0, right? So starts strong and starts to level off towards 0. Okay. And then here, from time t is equal to 0.5 to t is equal to 0.6, we have the negative derivative. Is negative. All right, and this means that our concentration starts to decrease. And so if we think about a drug in the bloodstream, we understand that if we take some medication, it's going to start at a concentration. All right, and it starts at the highest possible concentration until it starts to get less and less. All right, and your body uses it, or it does its job, and it starts to dissipate out of the bloodstream. So it's increasing in concentration, it levels off, and then it starts decreasing in concentration. So our values here make sense. All right, so that was our last example for section 2.2. Don't forget to take the comprehension quiz, and I'll see you in the next lecture.